you will see in the literature very often graphs of this kind. The energy I find somewhat suspect because it really is not energy, because this is not Hamiltonian. It has a part that looks like energy, and it inherited this part from Euler equations, which are Hamiltonian. Physical flows are usually not Eulerian. There is no variational principle, Lagrangian, that will give you these equations. They just came from phenomenology of flows, from statistical mechanics. So they are far from equilibrium when lots of energy is being pumped in, and the usual ideas are a little bit misleading. So the energy, I don't find it measurable in itself, but these fluctuations in power and dissipation, they're very physical. Typical results look like that. You plot here dissipation. You plot here, or maybe let's put dissipation here and power there. Here we put energy in, here we take it out. In the mean, they should balance each other. So we already saw this, for example, for traveling wave, we have that energy doesn't change in time, or equilibrium, because shape doesn't change. So in that case, these two quantities, which can be computed separately, must exactly cancel each other. So there is a diagonal. And if you have some equilibrium solution of your flow, meaning your flame front has some shape and it doesn't change in time, or it just rotates but doesn't change its shape in time, a rotating wave or traveling wave, then equilibrium solutions and traveling waves, they'll all sit on this line. And you'll give them some names. For a given physical flow, there is obviously some state which consumes least energy per unit time. And it turns out that state is almost always what's called laminar state. There is something which is lowest energy. Let's call it equilibrium zero. For a flame front, this was a state where U was constant. So all these gradients went away. And in that case, by Galilean invariance, we can say this to be exactly zero, and any fluctuation is higher than that. In flows like pipes or flows between planes, is the most regular state called laminar state, that is lowest energy. So it's natural to use it as a measure of dissipation and power. So usually you rescale your units of energy in such a way that your lowest state is unit 1. That means that if you're driving a Maserati at 270 kilometers an hour, and it's laminar, you have to use 1.3 gallons per whatever. However, if you enter turbulence, you will start dragging air, pushing it, shoving it, it will be shoving you, the energy will be radiated away. You'll be losing energy. You'll have more energy than you get viscosity. But on average, you'll be someplace here, and one of the predictions that good fluid mechanics or engineering should tell me is, if I want to move at 300 kilometers per hour, how much gas do I have to burn? Or how many kilometers I'll get per liter? And they'll sit someplace on the line, and one success of theoretical description of turbulent flows is that it will give that prediction. As it turns out, it does in a number of examples that are known so far. and does it rather well. So the average mean will be there. Then I defined the energy on periodic orbit as one of the possible observables. The mean energy is defined as one time period of your periodic solution. So, it changes its shape, does something, and after one period, you're exactly where it started, of the time average. And if I decide to look at dissipation rate, then this thing should be 0 for a long time, because if I'm in some steady turbulent state where I've let transients die out and I'm now on a strange attractor and I'm computing what the mean consumption is on it, then it cannot fluctuate in time. But if I look at time average of E in general, this will be 1 over T limit. T goes to infinity of 0 to T of this expectation value, which is time dependent, dot fluctuation around its mean. That should average to 0 for a long thing, because what I mean by steady state is that I put as much energy into it as I have to take out of it, and on average they have to cancel. So that means if I have some turbulent flow, what will happen in time is that I'll start with some state on my flame front, and then if it has some power, dissipation will work on it. I might get error wrong, but what this thing will do, it will fluctuate in some way that will be competition between pumping energy in and burning it. So if I get someplace up here, I burn a lot. If I get down here, I burn a little less. But on the average, the average of this time trajectory, defined here, will have to sit on a diagonal. So let's call this average dissipation rate, because dissipation rate will be 0, and its difference between power and that, then the mean power will have to be the same as mean dissipation. It will be point someplace here. So if you have a good simulation program, for example, in this homework, if you have Kuramoto-Shivashinsky equations, you can integrate them. This is the first thing you might want to compute. You might want to find out what is the mean energy and dissipation, and that's obtained just by integrating and taking the mean. That has to sit on this diagonal. And what you discover is something that engineers know very well. Our intuition in physics tends to be, if I change my parameter by 1%, then the consequence will change in some small way. We're used to the linear response ideas. So if I'm going 21 kilometers an hour and I would like to go 21.5 kilometers an hour, then I'll just change my gas pedal, burn the gas with 5% increase. However, it's not like that at all. If I'm in a laminar state, That's fine. That's working. But if the turbulence sets in, and that tends to be a sudden, sharp event, then I find out that suddenly I have to burn 4 times as much gas just to go half a kilometer faster. And, that's why turbulence as an engineering and human problem is a billion-dollar question, because anything we can do to decrease turbulent friction, dissipation in energy due to turbulence, translates itself in billions of dollars in energy savings, from airplanes to pipelines to anything you wish. So turbulence is not a small thing. Even when you change your parameters by very small amount, you change your Reynolds by something, small fraction, this can be 4 times as expensive to move, just a little bit more. So now the periodic orbit theory developed so far. I haven't at all explained that you can use it for partial differential equations, but I've shown you that the notions of equilibria and periodic orbits also exist for partial differential. There are such solutions also in infinite dimensional space. These things, if there is any truth to them, they should give us an estimate of how much energy I burn for a given physical system and given boundary conditions and parameters. And indeed, these plots will help you develop intuition. For example, you might find some equilibrium solution. So you might find that the first time that the flame does something interesting, so I might find that while for very slow input of gas, the flame was stationary, it might develop some instability. This will be some kind of traveling wave, and it'll sit someplace here. And you'll find these solutions, and things that you'll discover is that some of them, well, they're perfectly good solutions of your partial differential equations. When you compute their energy, they're very far away from the mean energy and fluctuations around it. If you remember what we did with Lorentz attractor and Rosslare, you should not be surprised at all. We found that Lorentz attractor, it had 3 equilibria. This is symmetric copy and one on the symmetry axis. They were analytically computable, but they had almost nothing to do with the typical motions. They were as far as possible from the typical motion of the system. They gave you some geometry scale where the things should avoid them. And that's what happens with lots of these equilibrium solutions, which I'll describe next, how you find them. They're very important to give you some intuition, but as they don't move and they tend to be unstable, they might turn out to be not at all good predictors of mean average dissipations, energy, and stuff like that. Now, in this course, we said equilibria are okay, but the important thing was really finding periodic solutions, unstable periodic solutions, because those were claimed to be embedded in turbulent flow.